Not sure if I'm like 40% battery, but the back will have the charger. So probably some relation, but I'm not sure.
Hi everyone, let's get started for today. Today we'll be talking about networks. This is going to be a two-parts lecture. We'll talk about networks, including trees today, looking mostly at topology, and then on Thursday, Carolina Norway, one of my PhD students, she just wrote a state-of-the-art report on multivariate networks and taught a tutorial at this about multivariate networks. And so I asked her to teach the Thursday lecture, where we'll talk about how do we analyze networks together with attributes. Before we get started, you should have heard by now from your TA and have gotten feedback, so you should know who your point person is for your project, and you should have heard whether your project proposal is in scope, and so on. So any problems, or anybody hasn't heard yet from the TAs? Great, so it looks like this is working out. So let's start to talk about networks. I want to just networks and graphs. First, I want to distinguish between what a network and a graph is and how I use those terms. But maybe even a bigger step back is what is a network? And I'm going to give you a colloquial definition here, and I'll follow up with something more formal later. But networks really model relationships between items. So what's a classical network everybody can think about immediately? Social networks, yes. Social networks, either social networks on the internet, but also social networks, everybody knowing somebody in this room here. So this could be like a non-computational social network as well. And so if we look at the dataset types according to Taraman's definition, we are kind of in this space here where we have networks with links and nodes. The nodes are the items here. And then we have a subclass of networks that are trees. And we'll talk more formally about all of this a little bit later. But now, why do I use the word network and why don't I say graph? You probably have heard of the field of graph theory, right? This is kind of the computational approach. How can we calculate shortest path or Hamiltonian path or anything like that? That's graph theory. If we talk about networks, we usually talk about a specific instance. So you talk about graph theory, but network data. So a social network, a biological network, and so on. And so since we most of the time care about visualizing specific networks, I've started using the word network instead of graphs. The other thing is that a lot of people who are not visualization people think of, if you say, I want to draw a graph, they think of any chart, right? And so I think that just helps disambiguate what you're talking about. So I want to start off with a little exercise and kind of get you thinking about how you can visualize a network. Here's a network with some attributes and nodes. So these are people, and then here we have links and link attributes that show whether these people have co-authored a paper and how frequently they have co-authored a paper. So I'm going to hand this out, and I want you to do two different designs. One of them should use this table here at the back, and then I want you to answer a couple of questions about that. And again, feel free to work in teams and discuss your designs. Okay, so I'm assuming that you're not all done, but you have thought a little bit about this. And so let me guess, most of you have drawn a network like this, right? That's kind of like a reasonable way to do it. And then I kind of like asked you to use the grid in the back. And then if you did that, you have probably created a network representation that roughly looks like this, right? Who has done both of those? Anybody? Yeah, okay, great. So leading questions lead to good answers. So now let's look at like the questions here. Like, if we want to ask how is Sean connected to Sylvia in this visualization here, how would you do it?
With the row labeled Sean, and then trace through the table until I find Sylvia, and then you have to look at what's in that cell. In this case, no.
So no, yeah, but I mean, like, what's the path between Sean and Sylvia?
Oh, I see.
Alex
I go back one slide and look at the other.
What did you say?
Through Alex and Mark.
Through Alex and Mark, yeah, but how do you, like, how can you read this from this chart?
Not easy.
Not easily, yes. So you can do it, so, but this kind of question is easily answered with this node link diagram, right? So how is Sean connected to Sylvia? We can simply find a path or the shortest path between them. So if we ask, like, who has the most connections in this network, we can answer this with this chart, but we can also look at this chart here. Like this, in this visualization, we simply look at who has the most filled out cells in a row or in a column, right? So that's actually quite easy to do with this particular representation. If we ask which two authors collaborate the most, that's kind of like an edge attribute question. And so here, if I did a little bit of a better visualization, like I can, the answer here is Mark and Alex, and so this would be 14. But if you use the heat map here, instead of me just putting in the numbers, this would pop out pretty well, right? So we would see like a dark spot here or some like unique color, and we could easily spot that. And here we could do like either labeling or we could do edge weights as they are shown here. And then finally, which author is only loosely connected to the network? So which of the two visualizations can answer that better?
This one.
This one here makes it easy to spot. How would you do this in this one? Like, how would you spot a node that is only loosely collected in this one?
That's a few squares.
Yeah, so if you have very few squares, and so you can see Sylvia has only a single square filled in, and Carolina has only a single square filled in. So if you know what to look for, this is also fairly easy with this particular representation. And kind of like, these are the two main representations for generic networks, like these explicit layouts, node link layouts, and we'll talk about how we can lay them out efficiently, and then the adjacency matches, which we'll also cover in more detail today. So let's take a step back, though. Like, I want to talk about networks and some kind of network properties first before we start talking about network visualization. Networks are really like underlying much more than you might think initially. So without graphs or network, we wouldn't have things like social networks. We wouldn't have like navigation applications, because if you think what a navigation application does, if you want to navigate from point A to point B, it simply treats streets here as edges and finds the shortest path connecting those 2 points. And it uses weights for example, in roads. Like, is it an interstate? That means I can go faster. That means I can adjust. Like, I'm calculating the time it takes instead of just the distance and so on. Any computer circuit is basically a network layout, but also the whole internet and algorithms like PageRank rely on that. Is one big network. So we kind of need networks in our daily lives. Here's a visualization of Facebook friendships, which was done by a Facebook student intern at one point. So if you look at this network, what can you see? China is missing. Yeah, so you can see, like, basically, you could argue that this is largely a population map, right? You don't really see all that much network structure, but you can see these interesting outliers, like like China is missing because of censorship, and you kind of see, like, even in the US, you see the typical pattern of dense East Coast, pretty sparsely populated West Coast. But this isn't necessarily a great network visualization, right? Because it doesn't tell us anything about the network structure other than where the nodes are. And we see that, like, well, kind of the connections between maybe like Hawaii to mainland US are fairly strong, about as strong as between like the US and the UK. So yeah, we can look at networks like this, but we'll talk about visualizations like this in a minute. Another big area for networks and a lot of network research, and also where I've done a lot of work, are biological networks. So biological networks can be things like interactions between genes and proteins and chemical products like drugs or any kind of compounds that you have. It's also like how our brain works. We have like a big neural network, not an artificial neural network, but a real neural network. And we have these connections between the neurons. And so on here is an example that actually visualizes the 3D spatial structure of a neuron that was reconstructed from microscopy. But this is kind of like a very complex 3D thing. And then on the right, here's an equivalent representation that is functional, that really only looks at network relationships. So like this one neuron here has all of these branches going off, and at each of these white dots here is a connection to another neuron. So that's kind of like an abstract representation of the same network. All of you have ancestors, and the ancestors between, like the relationships between you and your ancestors and their relationships amongst themselves is, of course, like a network. And so in Utah, we have this great resource to study population genetics, the Utah Population Database. So like there's a lot of work going on studying like data, genetics in the context of ancestry, in the context of these kinds of networks. And then we have phylogeny, the tree of life, where you kind of like have evolutionary relationship between species, and this is like a massive, massive tree, very complex, and that's like a subject of study, and like these are all prime targets for visualization research projects. Here's an example. This is like a pathway, a biochemical pathway that shows some kind of like metabolic process in the human body, and this is actually from a poster that I did have on my wall during my PhD, and you could walk up to this poster and look up this particular protein, and then it would have like something like A5, and you would find A5, and then you could trace where all of the connections are. So this is wall-sized with knowledge of 2002. Things have become more like we understand things better now, and these networks are even more complicated. Social networks are, of course, like we use them a lot, but we can also study some like pretty complicated effects based on social networks. And so the whole field of network science is concerned about like doing data analysis of networks. And here's like a brief TED talk. I just want to show the first 5 minutes of this to give you an idea of what kinds of questions you can answer with social networks.
For me, this story begins about 15 years ago when I was a hospice doctor at the University of Chicago, and I was taking care of people who were dying and their families in the south side of Chicago. And I was observing what happened to people and their families over the course of their terminal illness. And in my lab, I was studying the widower effect, which is a very old idea in the social sciences, going back 150 years, known as dying of a broken heart. So when I die, my wife's risk of death can double, for instance, in the first year. And I had gone to take care of one particular patient, a woman who was dying of dementia. And in this case, unlike this couple, she was being cared for by her daughter. And the daughter was exhausted from caring for her mother. And the daughter's husband, he also was sick from his wife's exhaustion. And I was driving home one day, and I got a phone call from the husband's friend, calling me because he was depressed about what was happening to his friend. So here I get this call from this random guy that's having an experience that's being influenced by people at some social distance. And so I suddenly realized two very simple things. First, the widowhood effect was not restricted to husbands and wives. And second, it was not restricted to pairs of people. And I started to see the world in a whole new way, like pairs of people connected to each other. And then I realized that these individuals would be connected into foursomes with other pairs of people nearby. And that in fact, these people were embedded in other sorts of relationships, marriage and spousal and friendship and other sorts of ties. And that in fact, these connections were vast. And that we were all embedded in this broad set of connections with each other. So I started to see the world in a completely new way, and I became obsessed with this. I became obsessed with how it might be that we're embedded in these social networks and how they affect our lives. So social networks are these intricate things of beauty. And they are so elaborate and so complex and so ubiquitous, in fact, that one has to ask what purpose they serve. Why are we embedded in social networks? I mean, how do they form? How do they operate? And how do they affect us? And so my first topic with respect to this was not death, but obesity. And it had become trendy to speak about the obesity epidemic. And along with my collaborator, James Fowler, we began to wonder whether obesity really was epidemic, and could it spread from person to person, like the 4 people I discussed earlier. So this is a slide of some of our initial results. It's 2,200 people in the year 2000. Every dot is a person. We make the dot size proportional to people's body size. So bigger dots are bigger people. And in addition, if your body size, if your BMI, your body mass index is above 30, if you're clinically obese, we also color the dots yellow. So if you look at this image right away, you might be able to see that there are clusters of obese and non-obese people in the image. But the visual complexity is still very high. It's not obvious exactly what's going on. In addition, some questions are immediately raised. How much clustering is there? Is there more clustering than would be due to chance alone? How big are the clusters? How far do they reach? And most importantly, what causes the clusters? So we did some mathematics to study the size of these clusters. This here shows on the y-axis the increase in the probability that a person is obese given that a social contact of theirs is obese. And on the x-axis, the degrees of separation between the 2 people. And on the far left, you see the purple line. It says that if your friends are obese, your risk of obesity is 45% higher. And the next bar over, the orange line, says if your friends' friends are obese, your risk of obesity is 25% higher. And then the next line over says if your friend's friend's friend, someone you probably don't even know is obese, your risk of obesity is 10% higher. And it's only when you get to your friends' 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 friends that there's no longer a relationship between that person's body size and your own body size. Well, what might be causing this clustering? There are at least 3 possibilities. One possibility is that as I gain weight, it causes you to gain weight, a kind of induction, a kind of spread from person to person. Another possibility, very obvious, is homophily, or birds of a feather flock together. Here, I form my tie to you because you and I share a similar body size. And the last possibility is what is known as confounding, because it confounds our ability to figure out what's going on. And here the idea is not that my weight gain is causing your weight gain, nor that I preferentially form a tie with you because you and I share the same body size, but rather that we share a common exposure to something like a health club that makes us both lose weight at the same time. And when we studied these data, we found evidence for all of these things, including for induction. And we found that if your friend becomes obese, it increases your risk of obesity by about 57% in the same given time period. And there can be many mechanisms for this effect. One possibility is that your friends say to you something like, they adopt a behavior that spreads to you, like they say, let's go have muffins and beer, which is a terrible combination. But you adopt that combination, and then you start gaining weight like them. And another more subtle possibility is that they start gaining weight, and it changes your ideas of what an acceptable body size is. And here what's spreading from person to person is not a behavior, but rather a norm. An idea is spreading. Now, headline writers had a field day with our studies. I think the headline in the New York Times was, are you packing it on? Blame your fat friends. What was interesting to us is the European headline writers had a different take. They said, are your friends gaining weight? Perhaps you are to blame.
Okay, I'm gonna stop this here. But yeah, you get the idea of these network effects and how ubiquitous they can be in a social network. So before we start to talk about network visualization, I just want to talk about a couple of graph theory basics. And I recommend this book by Albert Laszlo Balabazi, which kind of introduces network science and how you actually study these effects that the guy in the TED Talk just described. Okay, I think I screwed up my headline here. Well, anyways, you've heard of the, probably you've heard of the 7 Bridges of Kaliningrad. This is kind of like the historical foundation of graph theory happened there. And so what's the story here? Königsberg, which is nowadays Kaliningrad, which is historically Prussian and German, but now part of the Russian enclave. And the city had a river flowing through it, and then there were 2 islands. This here is an island, and this here is an island. And these islands were connected by 7 bridges. And so people started talking about, can I take a stroll where I cross all of the bridges, but none of them twice? So what's the answer to that?
Oh.
No, you can't. And so why is that problematic? Well, first, does it matter which path you take on land? So whether I take this street or that street is completely irrelevant, right? And so Leonhard Euler discovered this. We can kind of like abstract the islands into nodes and the bridges into vertices. And what we get then, if we do that, is we get a network like this. And he did show actually that taking a stroll like this is only possible for graphs with at most 2 nodes with an odd number of links. So if you try to do this in this graph and trace it and visit every edge or pass over every edge, you will find it's impossible. If you change this graph slightly to remove this one edge here, you can actually do it. So like I'm starting here at this network, and I might get it wrong initially, but let's see. Okay, I started here, I take this bridge, then I take this bridge. Oh, I screwed up. Okay, yeah. I get around here, take this bridge, back up here, down here, back up here. So that worked, right? So I can actually do this in this particular network when I remove this one bridge. And if you look at this, does this meet this property at most 2 nodes with an odd number of links? Yes, I have only one node, I have 2 nodes with an odd number of links, this one here and this one here. Yeah?
So did Euler then go out and destroy one of the bridges?
That's a good question, but I don't think so. A related problem is what's called a Hamiltonian path. So it's a path, you might have heard of this, that visits each vertex exactly once, and that's kind of like a computationally hard problem. Okay, that wasn't really intended either. Okay, so more formally, like if you talk about a graph, we can define a graph as a G of V and E, where we call V the vertices, and vertices and nodes are interchangeably, and E the edges, which we also call links. So you can use either of those connecting these vertices. And so here's like an example of a general graph. If a special kind of graph is a simple graph, and a simple graph is a graph that contains no multi-edges and no loops. So here we have loops, I mean self-edges. So this here would be like a loop, and this here would be a multi-edge. So this is a general graph and not a simple graph. Then graphs and edges can be directed, right? So like I can distinguish between a connection between A to P and B to A, or I can have an undirected edge, A to B. Can anybody give me an analogy for like an online social network that uses undirected and directed edges?
You follow someone, but they don't follow you back.
Yeah, so which social network is like that? Twitter, yes. And which one has undirected edges?
Facebook.
Facebook, yes. Facebook always assumes that friendship is mutual, and Twitter, you can follow people, but they don't have to follow you back. Some of you might have heard of the term hypergraph. A hypergraph is a graph where edges connect any number of vertices. And so this is important. This is not a path, but really the edge connects all of the vertices at the same time. And I usually think of this as sets. So these nodes have some shared property. And so, like, for example, if these were people and they all went to the same like university, they are all connected by this one hyper edge or by this one set. And then we can also define things like an independent set is a graph that contains no edges, or a clique, which is kind of like more common, is a graph that contains all possible edges. So a completely connected graph is a clique. And you could have like cliques as substructures in a larger graph. An unconnected graph is a graph where I can't reach every node from every other node. So this here would be examples. I have like isolated nodes, or I have isolated components, and I cannot actually traverse this graph from like any source point. And an articulation point is like an important node in a network that if it were deleted, would make a connected graph into an unconnected graph. So in this example here, if I were to delete the red node or the red vertex, it would break up this network into those two networks, and these kinds of things like articulation points are important to study or to kind of identify, because if I have, for example, like a communications networks, I want to avoid articulation points, and I want to make my network robust against the failure of individual nodes or instances. A biconnected graph is a graph without any articulation points. So here I can delete any node and it will not break the graph apart. And then a bipartite graph, or more generally a k-partite graph, is a graph where I can partition the nodes into two independent sets and I have edges only between A and B, but between the two sets, but not within themselves. This seems like a little bit esoteric, but it's actually much more common than you think. For example, if you think of an author-paper relationship, then you have like an author writes a paper, the paper has an author, but the authors are not connected between each other, for example. Okay. Then a tree is a special kind of graph. Like the most generic definition of a tree is a graph with no cycles. So you can also recursively define a tree. It's a collection of nodes that contains a root node and 0 to n subtrees. And the subtrees are connected to the root by an edge. So here would be this recursive definition. Like you have a root and then subtrees, and those subtrees follow the same definition again. And strictly speaking, a tree doesn't have to have a root, but most trees are in fact rooted. In certain applications, we also distinguish between unordered and ordered trees. So if we think about these two trees here as unordered, then they would be equivalent, so it doesn't matter the order of E, F, G here. But in some cases, if I consider this as an ordered tree, then I would want to distinguish between those two. And these are kind of super important, of course, in all kinds of data structures. So if I want to do any search algorithms based on a tree, then I will always work on an ordered tree. Yeah.
What would this tree look like without a root node?
Without a root node, oh, you can basically you can make any node root node, right? This is just a convention, and ideally it's semantically important, but I could drag B up here and have B be the root. Of course, in this case, the edges are directed, so that wouldn't work quite as well, but here would be an example of a tree this is a tree, but it's not obviously rooted, and here is kind of like the same tree that is rooted. So it depends on which definition you're in. And many of these, I've just given you a couple of examples, but there is many tree and graph classes that are named, and there's books about this. I just want to these are the most important ones, and there's more literature if you care about this kind of thing. And so if we look at a network, we can kind of as for a tabular data set where we can calculate histograms and look at some aggregate representation of it, we can also look at some summary statistics of networks. The typical summary statistics of a network is the number of nodes, the number of edges, and then also the degree distribution is a very frequent one. And so what's the degree? The node degree is the number of edges connecting a node. And so if I have two edges originating from a node, or then I have a degree that this node has a degree of 2. For directed graphs, I calculate or I measure in and out degree separately, and I can calculate average degree very simply, and I can also plot degree distributions. And so here is 2 networks and their degree distribution. So here you see we have this kind of the node number 2 here has a degree of 3. And the nodes number 4 and 3 have a degree of 2, and 1 has only a degree of 1. And so we see that node 1 has 25%, 25% of the nodes have a degree of 1, 50% of the nodes have a degree of 2, and then a quarter has a degree of 3. So this is how you would read this kind of degree distribution histogram. And it turns out that many real-life networks are A, pretty sparse, and B, have like a very, very skewed degree distribution. So here, this is a real-life protein interaction of a yeast, of the yeast organism, and you can see that the majority of the percentage of nodes of that degree is that we see that almost 50% of the nodes here have a degree of 1. And that we have only very few nodes that have a pretty high degree. These are the central hubs. And that's kind of like a common behavior in many real-life networks. So degree is kind of like a measure of local importance in my local neighborhood. So this here is a network that we'll be looking at quite a few times. This is like the characters of Les Miserables and how they are connected by co-occurrence in the book. And you can see that we have like the main character, Valjean, here in the center, and he's like, the nodes here are scaled by the degree. And we can see he connects broadly across this network, but here we have Muriel, who is connected only to Valjean of the rest of the network, but then has like this group of people around it, right? So she's locally important, but isn't all that important in the overall network. We'll talk about another measure in a second, but that gives us a global importance of a node, but to talk about this, we first have to talk a little bit about path. So, like a path is a route along links between two nodes, and the path length is the number of links that it contains. And very frequently in a lot of applications, we care about finding the shortest path that connects two nodes. What are like algorithms that I could use to find the shortest path between two nodes? Extra. But is there an easier one if I just give you topology?
Breadth first search.
Breadth first search, yes. So breadth first search is like a very efficient algorithm for, like if I don't need to consider network weights, Dijkstra's algorithm is useful for weighted networks.
And all the weights are positive, right?
Yes, when all the weights are positive. Then otherwise it gets a little bit trickier. And then of course there's many other algorithms. If you have some heuristic, for example in motion and pathfinding, you can use some kind of heuristic functions to get more efficient solutions and so on. Like the diameter of the graph is also another metric that we sometimes care about, is the longest, shortest path within G. And so we can use path to derive a measure that's called betweenness centrality. And betweenness centrality is a measure of how many shortest paths pass through a network. So you calculate all of the shortest path between all pairs of nodes, and then you measure how many of those shortest paths go through a particular node, and that gives you a measure of global importance. And so what you see here is that Valjean is still like the biggest node by far because there's a lot of shortest path going through him, but Muriel actually is still quite important here because she kind of connects all of those people, but then we see that other people down here that were that had a pretty high degree, they are kind of like redundant in this network, and so are not quite as important. And so if you compare degree versus betweenness centrality in a histogram, you will see that the degree, like even though degree distributions are often skewed, like betweenness centrality is often even more skewed. So you have like a few nodes that are very important according to betweenness centrality. I'm sorry about this projection thing. Yeah.
So with that graph, how do you determine that they're connected? Is it that they're mentioned in the same sentence with Les Miserables?
Yeah, I actually don't recall exactly, but it's probably something as have they like had a dialogue or have they played in the same scene. This is from like I think Tannenbaum had this graph extracted in one of his books. So that's just like a toy example that people use. Like the cars data set for multi-attribute data, this Les Miserables network is the standard data set that people use to demonstrate network layouts and so on. But yeah, like how do you come up with a network? That's an interesting question, yeah.
In the betweenness centrality, what happens if the shortest path, like there's two shortest paths?
Yep.
Do you, like half count a node or?
Yes. So if you have two shortest paths, that's a detail of the implementation. You could give it half a score, half a point. I'm sure there's variations of that. So yeah. Okay, so like that's the background on network science or graph theory. And now I want to talk about network and tree visualization. So as any visualization, it really like everything here depends on the data and the task. So we have different, like as I kind of like hinted at with the initial exercise, depending on the question you asked, you have different representations that are ideal for answering the particular question. So how do we decide which representation to use for which type of graph in order to achieve which kind of goal is kind of the question that we'll be answering over the next half hour to an hour. And so here's a paper that is like pretty short actually, 4 pages, but it lists all the kinds of tasks that you can like do on a network. This is a task taxonomy for graph visualization, and I think this is a pretty good paper to simply talk about topological tasks, and we'll talk more about what I mean by that in a second. So we have 2 principal types of tasks: attribute-based tasks and topology-based tasks. So attribute-based tasks would be something like, what is the value of this node? So if we have like people, what is the age of this node? Or what is the average age of this clique of friends? This would be attribute-based tasks. Whereas topology-based tasks are things like, how are those 2 people connected? What is the shortest path between them? Where is like this, is there like a clique in this network? Any kinds of questions about graph structure. So for example, if you want to localize, find a single or multiple nodes or edges with a certain property, you could formulate this as an attribute-based task. So for example, find the edge with the maximum weight, or you could also formalize this as a topology-based task, find all adjacent nodes of a given node. So like the main thing here is really the distinction between attribute-based and topology-based tasks. Like here would be like finding neighbors of nodes is like a classical topology-based task. Identifying clusters or communities is a classical topology-based task, but I could make this into, let's say, a hybrid task by saying, find the cluster or community of people that all went to the University of Utah, right? So that would be kind of like a hybrid task. Or finding path, I could equally say, find a path that only on edges with a certain type. Or I could just say find a path in the network and completely ignore any attributes. And so if you think about network visualization, there are 3 main approaches. These explicit layouts or node link layouts that we kind of all think of when we think about network visualizations, adjacency matrices, and implicit layouts, where I should say though that implicit layouts only work for trees. And so we'll cover that at the end, but there is no reasonable implicit layout that works for a general graph. So we'll start with explicit node link layouts. So here's our classical node link diagram. I have like my nodes are represented as the mark here is like a dot, and then the edge mark is the line or could be an arc. And I kind of like have a couple of choices on how I lay out my network, right? I can do like a completely free layout when I really want to emphasize the topology, like here in this case, or I could have like some kind of pattern that I use to lay out my network. For example, here I arrange all of my nodes along a circle. So then I have a style layout and all of the edges are guaranteed to be within that circle. Or I could lay out the nodes along a grid here. And then sometimes I also have a fixed layout where the nodes are given, the position of the nodes are given. For example, like typical context here is some kind of geospatial network. If you want to show like friendships, as we saw in this Facebook map earlier, on top of geolocation, you cannot actually choose the position of the nodes, but you have a fixed layout and you have to kind of worry about how can I route my edges so that I still see some structure in this network. And so, like, if you thought a little bit about these node link layouts, you could probably come up with a couple of like what makes a good node link layout. And it turns out that you can come up with a lot of optimization criteria. You definitely want to minimize edge crossing. You want to minimize the distance between neighboring nodes. You want to minimize the drawing area. I don't have like a finite space to show a network. Edges should be about equally long. I do not want edges to bend that much, and I especially don't want them to be bending in multiple high order. I want to maximize the angular distance between two edges because that way I can easily tell them apart. I want an aspect ratio of about 1 in my 2D layout so that it's not too long or not too wide. And then, like a little bit complex, I want symmetry. Like I want the clique to look the same wherever it appears in the network. I want like some kind of other sub pattern to look consistently the same no matter where it appears. And as you might guess, like there's many others, and there might be domain-specific ones. As you might guess, it's really hard to find, like it's actually impossible to find an optimal solution based on that. And so you kind of have to like find trade-offs. And we have these conflicting criteria. For example, here, for this network, if I want to minimize the number of edge crossings, I can draw it like this, right? And I have this edge here connecting the light gray nodes, but this is a very long edge. It's also bent, so it kind of violates these other two layout criteria. Whereas try to like not bending and having uniform edge length approximately, I could lay it out like this, but then I have edge crossings here. So that's kind of a trade-off. Or here in this tree, I want to optimize space utilization and maximize angular distance, versus I want like every parent and 3 children to look exactly the same for symmetry purposes, right? So these are obviously conflicting criteria, and I have to make choices about these kinds of things. And so one classical approach to creating those layouts is really to formulate the layout problem as an optimization problem. So you write some cost function that, for example, considers edge crossings and uses drawing space and so on. And then you simply throw a standard optimization techniques like simulated annealing at it, and you find a layout that minimizes that cost function. And you can, of course, like use any weights. For example, if you say, hey, edge crossings is super important to me, or like, I have some domain where I need like minimize my drawing space, then you can kind of like do that by weights. So that's a feasible way to create those network layouts. The other like main stream way to create network layouts are force-directed layouts. And so force-directed layouts, we've covered this a little bit in the D3 networks lecture, are based on like a physics model. So here edges correspond to, like in our mental model, to springs that pull two nodes together, and the vertices themselves are repulsive magnets. So two like not connected nodes will try to push themselves apart, and the spring forces usually are stronger than the repulsive forces, so that the nodes that are connected by the springs are pulled together. And so by using this kind of simple physical analogy, you can now run a simulation, and you can like iteratively create a layout. And so how does this work in practice? So you could initialize your vertices in random locations, and then you run a loop while not in some kind of equilibrium. I calculate the forces on each vertex by summing the pair as repulsion of all nodes. So I have to like really compute, well, how much do they repulse each other? And of course, repulsion decreases with distance between two nodes, and then the attraction between connected nodes. And then I move the vertex by this force accordingly. So if I get a vector out of this, and I move this vertex over, and then I keep doing this and doing this and doing this until some kind of equilibrium is reached or some kind of termination criteria is reached. I could say do 1,000 iterations, or I could say if the sum of my movement is smaller than some threshold, then stop. And this is what this looks like. You've all seen this before. So we start with random locations. This is again the Les Miserables network, and it starts kind of like untangling itself. And we see some nice structures here, right? So we see like a clique here appearing pretty, like this is probably the clique that connects Muriel. And so here is Muriel, and you see that like they're nicely spaced out, and I see that structure. And of course, like this network here has really nice properties, and that really appears well with this particular layout algorithm. So what happens when there are no links? We've also seen this in the previous lecture. Because we have only repulsive forces, then things just like spread out continuously. Yeah?
Are cliques the same thing as clusters, or are they sort of a different
Yeah, a clique is actually strictly defined as a completely connected subnetwork, and a cluster is, or it's also called community in social network analysis. That's a little bit more of a fuzzy concept, right? That is really something that is tightly connected relative to the rest of the network, and so it's like clusters in any kind of data mining application. They're kind of not as well defined, but yes, finding clusters and finding cliques are related. Like a clique will always be also a cluster, or in many cases be a cluster, or at least part of the same cluster. So if we reflect a little bit on this force-directed layout algorithm, it kind of leads generally to a good layout. It also results in uniform edge length. Clusters are commonly visible. It is not deterministic, right? I have a random layout initially, so it's not guaranteed, or it's definitely not the case that I will reach the same layout if I run the same thing twice. And it's computationally expensive. O of n to the power of 3. So like, why is that? Because in practice, like in every step, I have to do pairwise, like I have to calculate the pairwise repulsion forces, which is n squared. And in practice, it takes about n steps to get into like a good equilibrium. And so that's where the n to the n cubed comes from. You basically can say on a modern computer in a web browser implementation, you can do this interactively for about 1,000 nodes. You can, of course, like do this for bigger networks if you pre-process it, but in something like D3 that you want to do on the front end, you can kind of like 1,000 nodes is where it starts to slow down. In practice, you also want a couple of other things to happen in this force-directed layout. You want some damping to simply reduce the amount of movement and the center of gravity. And then you also want usually some collision avoidance between the nodes. And so here's an example by Steve Harrows on how you can play with all of these different D3 parameters. So like the simple one here will be moving the center, and so all the nodes are also attracted to the center, or by changing here the charge, the charge of the attracting or repelling nodes. Then here I could, let's go smaller. If I, for example, were to not consider collisions, you can see that I have overlaps here. And then I can add other forces if I want to. And of course, I can vary the link strengths. So if I vary the link strengths, then that will also changes. So all of this is parameterized, and very often for a specific network, you have to play with those parameters to find a good layout. So what happens is, if you lay out a really big network, and you definitely can do that, is what you get is the giant hairball. And I always like to compare this visualization with the informational value of this picture here. So those are not necessarily the most informative networks. And so I'll talk a little bit more about what we can do about that. But first, if I really wanted to lay out a really big network, what would be an approach that I can do to improve performance here? And so what I could do is I could run a clustering algorithm first, and then identify clusters of my network, and then apply the force-directed layout only within those clusters and between those clusters. But in this case here, I'm never calculating the repulsion forces between this node up here and this node up here. I'm just calculating repulsion and the attraction forces between those clusters, right? And by breaking this down, I kind of make this problem a little bit more complicated. So I have these virtual vertices that I use, and that kind of helps me to scale up performance of some kind of force-directed layout. But more generally, if I have this big networks, do I really need to see the whole network? Do I really need to get an overview of everything? And so, there's kind of this alternative approach that, especially in networks, become quite popular is like the query first, expand on demand. It's kind of like really is asking the question, what do you want to know from a network? And an overview is rarely the thing that you want to know. So here's a tool that we built. This is like a co-author network here, and I could, for example, look for Maya. And here we have Mariah, and I can, like, this is a network with more than 20,000 nodes and 100,000 edges. And now I've only revealed, like, Mariah plus all of her papers. But I could also say something like, expand all of the children, and now I've retrieved all of her co-authors. And then I could continue, oh, I care about this guy, and then I care about, like, what is going on here. And all of this happens essentially by querying a graph database in the backend, right? It's like much more question focused, and it doesn't try to show you like a visualization of all of the computer science authors and all of their papers, because that might not be a question that you actually have. So these query-based approaches are fairly common in network visualization nowadays. Now, like another layout would be orthogonal layouts. And orthogonal layouts, they essentially have the rule that edges can only be either like horizontally or vertically. And so that has advantages. And this is very common in biology. These are not very connected networks. We have like these llamer paths. And so here we have 3 different layouts. On the left, we have a human curated layout. In the middle, we have like an algorithm that was kind of the state of the art before this particular paper. And on the right, we have an algorithm that this paper here developed. And so this looks fairly close to the human-generated algorithm. And so why am I showing this particular algorithm? Because I think, like, I don't want to go into the details of the algorithm, but I want to go into the details of how they actually developed the algorithm. And so what they did, which I found a really great idea, they did like a crowdsourced task where they gave people a network and then asked people to lay out that network. So they gave them something like this network here, and this network here, and this network here, and this network here. And so then like a lot of crowd workers got paid to lay out those networks and try to find an optimal layout. And then they gave, these were the kinds of like layouts that they got. So here you see like a lazy human, that has basically not changed as much. And then here you have like optimized layouts by humans. And so what they did is they got all of these layouts that humans have created and gave another set of people those layouts to evaluate them. And so now they kind of had judgments about what are the things that people consider to be good layouts. And then they kind of derived, like studied what exactly makes those layouts unique. And then they created this Hola graph layout algorithm on top of it. Unfortunately, there isn't an implementation of it available. I'm guessing it's pretty brittle and pretty computationally expensive, but still like a cool approach of how you can do like a formative study to optimize a visualization problem. So back like a couple of years ago, I got kind of like, I was in Cambridge, Massachusetts, and I got like 2 emails a month about somebody wanting to do network visualization in VR. Just because like, oh, network layouts are complicated and networks are important, can we not make it easier in VR or AR? And then I see things like this on Twitter, where people interact with a network in 3D. And why do you think this is not such a great idea? Well,
It seems like it would work if you have about 20 nodes, and not at all if you have any more than that.
Exactly. So we kind of like the scalability problem is much more complicated. Any other ideas why it's not such a great idea? Yeah, exactly. We have occlusion. Edges can hide an edge. Nodes can hide an edge.
So you have to wear the headset to do it, and so therefore you can't multitask or make notes separately while you're trying to interact with that.
Yeah, so you have all these typical problems of AR and VR. And one other thing that I think is kind of actually important is when I do a 2D layout of a network, I really optimize it for this one projection of it, right? But if I do 3D and I want to rotate it, I can't really optimize for every particular perspective on that network. So it kind of like forces me to get occlusion in that sense. And so 3D network layout, usually not a good, no, I've never seen a case where it was a good idea. But I'm not saying usually, but never a good idea. Like another thing that is useful is these style layouts. And so here, like this is a very simple case. We have a circular layout. All of the nodes here are just arranged on the circle. And as you can see, like it's kind of like hard to see a lot of structure here, but this and we have 3% of all possible edges, and it's already pretty cluttered. If we have 6% of all possible edges, we get into this black territory here, right? What we can do is we can optimize the node ordering so that nodes that are closely connected are close to each other. But there's something else that we can do, well, maybe like let me say one more thing. Like this is kind of useful when you have a node order that is meaningful. And so where you see this frequently is, for example, if you have the genome, which is a linear sequence, and then you want to show like relationships between parts of the genome, then people would arrange like the genome here on a circle and then show any kinds of connections between them. And that's because like the position of like the sequence of the nodes is important. That's when these kinds of layouts are useful. What you can do is edge bundling. That's kind of like a pretty cool idea. So here you have, this is a software visualization. This is like, I think the Flare visualization library, which was a Flash-based visualization library. And you have like folders, packages, or classes, and then individual functions here. So 3 levels, a hierarchy, and then you have calls between those different pieces of code that are visualized here as the edges. So this is a network. We have the circular layout, and then we can use edge bundling, and we get something like this. And so this is kind of like, now we can see here pretty well that this here seems to be like a pretty central module of this software package, and we see that it interacts a lot with these pieces of code up here, and then a lot with these pieces of code up here. We can see a little bit of this, of course, here as well, but this is like a much cleaner idea. And so how do they do that? I guess, yeah, that would be like a little bit easier if I drew, but I'll just draw it like this. So like the idea behind this is that you, like if you look at this, is that you have, this hierarchy here, right? And so what happens is that if you look at this network here, is that things are bundled according to the hierarchy. So like we have like for every hierarchy, we have like one interpolation point in here, and then all of the elements that are in this hierarchical subset are bundled around here. And then we have the larger hierarchy up here, and this is somewhere bundled up here. And then these are kind of like our support points. This is what you can see here. So you have like a node that wants to connect from here to here, and this is like the backbone hierarchy. And what you do is you simply trace it along the hierarchy, but you use this as a support point for a spline, and this is how you get this bundling. And so, as you can imagine, like I can parameterize this, like how like this spline, and then I can like get a couple of different bundling strengths here. And so that would be kind of like the backbone that I just mentioned. That would be kind of a representation of that. Like here would be like this would be the nodes. Then here we would have the point representing the first level hierarchy, second level hierarchy, third level hierarchy. And so we can route along those paths and then get this hierarchical edge bundling. This is like a super popular paper. Here's a couple of variations of bundling strength. So like the beta factor is what they call it here. If I have no bundling strength, it looks like this. If I bundle it extremely, I mostly see the hierarchical backbone. So in practice, you want to be somewhere in the middle. And so in V3, this is nicely implemented. And I can kind of like change this tension, this beta factor here dynamically, and change it from like a completely not bundled layout to extremely bundled layout. And so like probably the best layout is somewhere in the middle here. Okay, fixed layouts as I said, are really typically done on maps, but there's also some like attribute-driven positioning cases, which we'll talk about on Thursday, where you want to do that. And like this is really messy because you cannot optimize your node placement. You often have like this very like extreme occlusion in these networks, and you could do something like bundling as well. Here the bundling works a little bit differently, and this is much more computationally expensive. What they do in this example here is they take each link, partition it into smaller segments, and then treat those in a force-directed, like in a physics simulation where link segments that are close to each other attract each other. And so this way you get these bundles in, even if you don't have like a hierarchical backbone. That's very computationally expensive, and I'm generally like a little bit skeptical whether this is a super useful representation for a cloud network like this. But this has been like a lot of people have studied 15 different variations of these bundling algorithms. So there's many papers about this, and some people really like make a career out of just developing new bundling algorithms. One super important thing to deal with scale is aggregation. And so here is an example of like using what's called a supernode. And a supernode is an aggregate of nodes. And so like here in this case, I have the black nodes are my like basic nodes, and then I have these like colorful circles that I want to define as supernodes. And so I could say something like, I want this group of nodes to be my gray supernode, this set of nodes here, my yellow supernode, my blue supernode, my green supernode, and I can then create this abstracted graph, this aggregated graph. And the question is, how do I define those supernodes? I could use some community detection or graph clustering algorithm, or I could let people define what is in a supernode manually and then collapse it. And essentially, like what you get is you summarize like between a supernode and its adjacent supernode, if there is any edge between them, you draw the edge, and then you can also add weights if you want to show how many edges are connecting between two different supernodes. So here's an example of how this is done, and I think this is a pretty cool example of how you can use like a spatial fixed layout. So they do a couple of smart things here. So this is like a similar data set to what I actually showed earlier with the force-directed edge bundling migration patterns in the United States. They do filtering here. They do interactively only show edges within those rectangles that they have drawn. And so you can see like what are the patterns between Washington, Los Angeles, New York, and Florida. So that's the first thing that they do, which I think is pretty smart. But then they can turn these like areas here into supernodes. So basically they say like this larger metropolitan area, I treat them now as supernodes. And you see here now that Washington area is like there's a lot of people migrating within Washington. So migrating, but are staying within Washington. There is a lot of in-migration into Washington from New York. And by using these very abstract nodes, they now have space to show us something about the nodes that are contained in here. So they show like histograms and some kind of other plots on top of these nodes here. So kind of to wrap up explicit representations, the pros of explicit representations, aka node link diagrams, are that we can visualize all kinds of graphs, all graph classes. We can customize the layout by weighting our layout constraints. We can say certain things are more important for our layout than for my case and for others. They're very well suited for topology-based tasks. So every time I need to detect, like find a path, they are kind of like the best choice. Of course, limited by the number of nodes, and of course limited by the layout that I choose. And cons is that like these force-directed layouts and also the optimization approaches are pretty computationally expensive. And heuristics are still slow. Like optimal graph layouts is NP complete. The heuristics are still slow, like typically and cube, and it has a tendency to clutter. So we have pretty limited scalability of that. Okay, so any questions about node link before I move on to adjacency matrices? Okay. So, matrix representation. So, like matrix representations are probably not quite as familiar as node link diagrams. So here's the equivalent node link diagram and an adjacency matrix. And so what happens here is that like A has a connection to B and A has a connection to C. And so we see that A here is like a filled-in cell for the B intersection and for the C intersection. And this is an undirected network, so it's symmetric around the diagonal. So if you look like above and below the diagonal, it's completely symmetric. If I had a directed network, I could say like I have from in the rows and to in the columns, and then I would have an asymmetric representation in the matrix. And so matrices can take a little bit getting used to. Here are some pattern or some graph structures and some examples of how they look like. Or how they can look like in an adjacency matrix. So here we have a star, so X is connected to all of those nodes. That's simply like a column here. Here we have like, this is like a directed network in that case. So if this is completely connected but directed. So we see like this piece here, if this were undirected, this would be like a blue square. Here we have like a set of bipartite connections. A and B are connected to C, D, and E, but those two groups are not connected with within each other. So this is what this looks like. And then here we have like some more general graph. So we get these structures and patterns that we can try to spot. But pathfinding is kind of like the main weakness of adjacency matrices. So for example, like they're really great for spotting neighbors, much better actually than node link diagrams, especially when it's cluttered or something like that. I simply have to look through my row and I can spot whether a node is connected to another node. But they're really bad at path tasks. And so that's kind of like the main weakness of adjacency matrices. So if I wanted to find for this network here, if I wanted to find a node from like a path from A to B, I would have to sit down and kind of like use a pencil to kind of like highlight where are the connections. It's possible, but there's like a lot of research that shows that it's slow and people make a lot of errors, and it's just not really a good idea. Here's just an example of how a larger network looks like in an adjacency matrix. And so we have like down here is a clique, and this clique here is like basically a red square where every cell except for the self edges are filled in, and then we have bi-cliques here, so they look like this. And so what you see here is that we have like a lot of stuff along the diagonal. That is not by accident, because somebody has like carefully sorted this particular adjacency matrix. And that kind of like gets me to the point about adjacency matrices. This is like for any like the heat, we talked about heat maps. The same is true for adjacency matrices. The order is critical, right? So here I have my Les Miserables network, and it's ordered alphabetically. And then here is the same network that uses a matrix seriation algorithm to kind of like put neighboring nodes or communities together. And we can very quickly see that there is a lot of communities. Like we have all of these yellow ones here, the violet ones, the red ones, and then we have like this cluster of green and orange ones. And then we also spot quickly the super highly connected nodes. So this one here, you might guess, is the main character in Les Miserables. It's Valjean, and then we have the other like person that kind of like appears a little bit more here is Javert here. Like you see some, well, with my highlight it's a little tricky to see, but you can see that Javert is also somewhat connected. So you see some of those star patterns appear as well. And so, well, let me show this example. Like you've seen this probably. But yeah, here you have the Les Miserables co-occurrence network. Let me zoom out. And if I order it by cluster, I see these nice patterns. If I order it by frequency, I see a little bit, but not quite as well. And if I order it by name, I basically have like a random order, and that is not particularly useful. And so there are, like, for web based implementations, there is a library that's called reorder.js that has a lot of different of these matrix seriation algorithms built in. And depending on like which kinds of patterns you want to see, you should use different algorithms. So on the pro side, matrices can represent all graph classes except for hypergraphs. It puts the focus on the edge set. Something that I haven't talked too much is like how we visualize edge attributes. We'll talk about this on Thursday. It is trivial to lay out because it's just a grid, right? So I don't have any complicated simulation that I need to run. It's well suited for attribute-based tasks on the edges. For example, by coloring the matrix cells or by changing the saturation of the matrix cells. It's well suited for neighborhood-related topology-based tasks, so identifying neighbors. Cons is you have quadratic screen space requirement, like every possible edge takes up space, and it's not suited for path-related topology-based tasks. So it depends a lot on what you want to do, but generally, I personally like matrix representations a lot. You can also try if you have a graph that has a lot of tight cliques or clusters. You can kind of do a compromise between a node length diagram and an adjacency matrix. This paper is node tricks. And so you see that they have chosen some kind of subset of the network to be represented as an adjacency matrix. This is similar to a supernode idea, right? But just that the supernodes here are the connections within the supernodes are also represented here by the adjacency matrix, and then you see the connections between those sub-matrices using a node link approach. One thing that you can also do is to make those more scalable, you can kind of roll up with supernodes again. So here, for example, if I have some hierarchical structure that I can derive, for example, from clustering, I can now say, hey, this I subset here, A, B, and C, that is fairly tightly connected. And so what I can do is I can create one representation for that instead of showing all of those individually. And that way I can save space, right? If I have some, think of this migration example, I could collapse all of the northwest and the northeast into one single cell and don't have to have every single state in here. So I can kind of roll this up at multiple levels if I wanted to. And then this is the project that we did. This is looking at some higher level connectivity. So if you think about, if you want to fly, for example, to some city, you might, from Salt Lake City, you're kind of in luck because there's a lot of direct connections, but there's not a direct connection to every single airport. And so if you want to look at some more abstract connectivity, how long does it take me, or is there a reasonable connection at all, then you can do path searches, and you can also represent this higher level connectivity in an adjacency matrix. And so here we're doing exactly that. We are showing at what are the connections between, let's say, Minneapolis and Portland, and we can see that there's a lot of possible connections if we consider 1, 2, or 3 hubs. And then we can see for this particular, for Sioux Falls to Portland, we can see that what are the different overlays. There's Atlanta, Denver, Salt Lake City, Phoenix, and so on. And then you can investigate all of those paths in detail. And these kinds of questions are for these communication traffic networks. They're relevant, but we actually did this as a case study for neurology. Okay, trees, I'll probably start covering them next Tuesday. On Thursday, I'll give Carolina time to talk about multivariate networks. Thank you guys, and see you on Thursday.